a bit of quantitative consideration. I will not derive it, but let me explain what it means. Recall that a polyatomic molecule has n atoms, 3n coordinates, and during the oscillation or during the vibration, each one of the atoms is expected to go away from its equilibrium position. So if you think of atom 1 as having a coordinate x1 equilibrium and its instantaneous atom 1, x1 equilibrium, and at any instant of time it has a position, an amplitude x1, the difference between the two, x1 minus x1 equilibrium, is the amplitude of the oscillation. x1 is a function of time, x1 equilibrium is not. x1 is x1 of t, it is a function of time. Therefore during the oscillation the x1 changes, and as it changes the amplitude, that is a vibrational amplitude which is increased, and then it goes to 0, okay, and it increases and so on. So this is for the x coordinate of the first atom, and likewise for the y coordinate of the atom, y1 y1e, and the z coordinate is z1 minus z1e. Now when you ask me what these coordinates are, if you have to ask me how do we define the axis system, let us assume that these axis system, the x, y, z axis, remains fixed at the center of mass of the molecule. This is a classical picture, please remember that. Okay. In quantum mechanics there is a problem in fixing the center of mass to a particular point if the total momentum of the molecule is conserved. There is a problem, let us not worry about that. Okay. Let us worry about the fact that we have the axis system fixed at the center of mass of the molecule, and we talk about the 3 coordinates of atom 1. Then with respect to the polyatomic molecule, if I may draw the picture, so let us assume that some 3-dimensional blob of a polyatomic molecule with various atoms in positions bonded to each other, and let us assume that the center of mass is somewhere here. We will draw 3 axis system. There are reasons, there are specific methods for assigning these axis systems, we will not worry about it. Let us assume as a first drawn picture that we can assign an axis system, and we can find out that how this atom goes away with respect to its equilibrium position during the vibration. That vibrational vector amplitude is projected onto this axis system into 3 components, x component, y component and z component, and let us call those as the 3 coordinates for atom 1. And likewise if we write for atom 2, similarly x2 minus x2 of E as the x coordinate, y2 minus y2 of E, z2 minus z2 of E, and likewise we can do this for all the n atoms. So we have 3 n coordinates which are likely to change during the vibrational motion of these molecules, 3 n coordinates. Therefore the potential energy of the molecule during the vibration is a function of all these coordinates x1 y1 z1, x2 y2 z2, xn yn zn. Remember this was not a problem for the diatomic molecule, because in the case of diatomic molecule we considered only the relative displacement of the atoms with respect to each other, 1 coordinate. Now we have got 3 n coordinates. The potential energy in the case of a diatomic molecule depended on that 1 coordinate in the form of kx square, where x is the amplitude of vibration. Now when you have a polyatomic molecule with 3 n such coordinates, you see that the potential energy is going to be a function of all these 3 n coordinates. Therefore it is a much more difficult function to write, and this is where the approximation of a harmonic oscillator like approximation comes in very handy. The normal modes, as you will see in a few minutes, are nothing other than the extension of the harmonic oscillator approximation of the diatomic molecule to harmonic motions of all the 3 n minus 6 degrees of freedom of a polyatomic molecule, restricted to quadratic in the amplitudes. Kx square is the quadratic in the amplitude x, and if you do that in the case of a polyatomic molecule as quadratic to every such atomic amplitude, then what you get out is the solution called the normal mode solution. This is all known in classical mechanics, and in quantum mechanics again you take this picture directly and then you construct the vibrational Hamiltonian and solve for the quantum mechanical normal modes of vibration for a polyatomic molecule. So if we have to write the potential energy as a function of all these coordinates, and let me write them as simply r1 vector, r2 or n. If we write this as n vectors, you see that for small amplitudes of vibration the potential energy is nothing but a constant value corresponding to this amplitudes all being 0. What is meant by that? Every difference, x2 minus x2e, y2 minus y2e, z2 minus z2e, likewise all the amplitudes are 0, V0 corresponding to equilibrium concentration, equilibrium geometry. Then we have sum over, let me not specify what they are, but sum over every coordinate, dou v by dou x I, xi minus xi e, sum over I equal to 1 to n, plus again I equal to 1 to n, dou v by dou yi minus yi. This is a Taylor series, plus sum over I equal to 1 to n, dou v by dou zi times zi minus zie, and what you have is nothing but the first derivative in the Taylor series of a multidimensional function, dou v, and if you extend this to the quadratic term, what you have is 1 by 2 sum over I not equal to j dou square v by dou xi dou xj xi minus xie xj minus xje, and you can write 5 more such products corresponding to yi yj, zi zj, then xi yj, xi zj and yi zj. There are 6 such terms, and this is called the quadratic term. It is quadratic because you see this is a constant evaluated at equilibrium. This is evaluated at equilibrium, therefore these are all constants. This is evaluated at equilibrium. Now if the potential is a minimum, is an absolute minimum, we have a way of saying let us ignore the potential V is equal to 0. This is again goes back to the harmonic oscillator model. We remember the force as minus kx, we integrated the force by writing them as the negative derivative of the potential, and then we set the potential at x is equal to 0 to be 0 as a scale. That is our minimum. And in the same way, if we assume that the equilibrium geometry has the smallest potential energy, let us assume that to be the minimum. Therefore with respect to the minimum, you remember the minimum is defined by the requirement that all the derivatives of the potential with respect to the first coordinate, as you have here this one, all the derivatives will also be 0. Gradient is 0 at the minimum with respect to that coordinate. Therefore if we write the potential energy using the small amplitude approximation as a Taylor series, this goes to 0 by our scale, this goes to 0 by the requirement that the potential is minimum, this goes to 0 by the requirement that the potential is minimum, and also this, and therefore the very first term that is non-zero is the quadratic term. Okay. The quadratic term unfortunately contains the x coordinate of one atom and the x coordinate of the other atom. It contains the x coordinate of one atom and the z coordinate of the other atom. Therefore, the quadratic is a mixed quadratic. The normal mode approximation or the procedure is a procedure by which we are able to rewrite this in the form of new coordinates which will contain only the squares of the individual atoms. When you write this V in the form of new coordinates q1, q2, q3n such that the potential energy is to first approximation nothing other than sum over I, a constant lambda I, q I square I equal to 1 to 3n, as opposed to what you have here. What you have here is a constant which is a function of the two labels atom I and atom j. This is a lambda ij equivalent, but now if we are able to do an analytic procedure so that this is changed into this new coordinate, so that the potential energy is nothing other than lambda I qi square, where now qi's are defined as the new amplitudes. This procedure is something that one can do analytically, there is no problem with that, and if we cannot do it analytically for large molecules, we can subject the procedure to a computer program and we can get the results numerically. You will see all the animations that I will show in the next few minutes are based on a procedure of converting them into this form. So what you have is H is nothing but sum over all the atoms of the individual harmonic oscillator I equal to 1 to 3n, except that now we have 3n coordinates, and therefore what we have is of these 3n coordinates, if we remove the 6 degrees of freedom for a non-linear system, we get 3n minus 6 normal coordinates corresponding to the qi. This is a very gross way of explaining things, but mathematically if we have to do it, it gets somewhat complicated. The procedures are well known. Now let us see for some real molecular cases what this will lead to for the vibrational motions of the polyatomic molecule. Let us see it one by one with a few examples. Okay. So what I have here in this program, I'm using a program known as Gaussian in chemistry. It's one of the most important programs in computational chemistry. For the discovery of this program, Professor John Popel from Carnegie Mellon University, when he did most of this work, got the Nobel Prize. He shared it with Walter Kohn for computational chemistry. Walter Kohn devised the procedure of what is called the density functional theory for computing the energies and the quantum mechanics of atoms and molecules. This is a program which provides you the animations and the calculations that are shown that use to provide you the animation. The calculations are all numerically very accurate calculations. So here what I have is the tetrahedral molecule of methane. Okay. Again you see that methane as is does not have a dipole moment, but there are going to be some vibrational modes in which the atoms change unsymmetrically and therefore dipole moments will be introduced. Let us see that by way of simple definitions, that this is a 5 atom molecule, therefore there are 15 degrees of freedom. 6 degrees, this is a non-linear molecule, tetrahedral, therefore 6 degrees of freedom go towards rotation and translation. There are remaining 9 degrees of freedom. The molecule is highly symmetric and therefore some of these vibrational degrees of freedom have the same energies and same frequencies. Let us look at this table, which is not very clear to you, but in this table there are 9 vibrational degrees of freedom, each with a vibrational frequency given here, and what is given here is the first 3 vibrational frequencies are the same, the next 2 vibrational frequencies are the same, this is different, and then there is another vibrational mode for which all the 3 frequencies are degenerate, but the vibrational motions will be different. Let us take the first one, 1373.5 centimeter inverse. Okay. We will start the vibrational motion and see what it looks like. So this is clearly the way you look at it, this is a bending motion. Look at it from any angle. You see that what you have here is the bending of two atoms, these two atoms in one plane and those two atoms in the other plane. You just look around, okay. This is clear in this view. The pair of atoms in a plane perpendicular to the pair of atoms in the other plane undergoing the bending motion. This is one of the normal vibrational modes for methane. Let's stop this, and there is another vibrational mode with the same energy. Now it's easy for you to remember that there should be at least two other modes. Let us look at why it should be. See what kind of bending that takes place. Which modes are bent here? See that these two atoms are bent, and this is the other vibrational normal mode. Let's look at what's the third one is. This is the third vibrational normal mode. So the bending about various axes, there are three such equivalent bending modes in this case. What about the next one? The frequency is now 1593 centimeter inverse, and again this is a bending vibrational mode. You see that these two bonds are bent and there are relative variations, positional angle variations in all of this. The bending motion is generally of a lower energy than the stretching motion. The stretching means you are stretching a given bond like a CH, which is fairly strong in energy. Therefore, let us look at one of the stretching motions and see what it is with a very high energy. You can see that this bond is being stretched, and likewise the other bond is being stretched, and there is a certain amount of synchronization. Look at it very carefully. All the four atoms are displaced from the equilibrium by the same, during the same time, by the same amount, because all four are hydrogens, same mass, and the positions of the atoms instantaneously at any point is such that you see that there is a dipole moment created during the motion. There is a net dipole moment which gets created, increases, and then it decreases to 0 and so on. Therefore, this is an infrared active mode that it can be detected using infrared spectroscopy. Now let me look at another such bending mode, another such the stretching mode, and what you see here is again the stretching of the atoms in a different way. There are very specific rules for determining these oscillations, these amplitudes, and these were given elaborately by Professor Hertzberg in his most famous the monograph on molecular spectroscopy. Professor Gerhard Hertzberg did most of his research on this in Canada. Let us look at one vibrational mode which is very interesting, namely the symmetric stretch. Let's look at that. All the atoms vibrate about, they breathe in and breathe out with respect to the equilibrium position, and in this motion of course there is not a single instant where there is a dipole moment. Therefore, there is no dipole moment during the motion, and there is no dipole moment for equilibrium structure of methane, and therefore this is not infrared active. This cannot be detected. This is for benzene, this is for methane. Let's look at some interesting case like the slightly more numerous atom molecule. Yeah, let's look at the normal modes of vibration of benzene. It's a very classic example, one of the most important aromatic molecules, of course. C6H6, 12 atoms, 36 degrees of freedom, 3n minus 6. Benzene is a non-linear molecule, planar in its equilibrium geometry, and what you have is 30 vibrational degrees of freedom. Also, benzene has a very symmetric structure, and therefore by the rule of nature, by the law of nature, benzene also has several vibrational modes which are degenerate. The important thing to note is that benzene does not have any vibrational mode which is more than doubly degenerate. The previous molecule that I talked about, the methane molecule, has 2 degrees of freedom which are triply degenerate because of a certain type of symmetry. The molecular symmetry and molecular vibrations are intimately connected to each other. It's not about, this lecture is not about it, but let us look at the benzene vibrational modes to see a little bit more about what normal modes are. So let me first locate a very low energy vibration, 414304, 0.304, that is 414 centimeter inverse. This is theoretically calculated numbers. There are 30 vibrational degrees of freedom. Let's look at the first one and start the animation to see how they look like. Okay, nothing seems to be happening on the screen, but if I just move the plane of the molecule to a slightly better perspective view, you can see that the atoms are vibrating. This is nothing but the ring, the benzene ring, getting distorted. Okay, see that 2 of the atoms come out of plane and the other 4 atoms remain, and this motion is such that there is no net dipole moment created, because whatever is the dipole that is created by these 2 groups is annulled by the other 4 groups. There is no dipole moment, therefore this cannot be detected by infrared spectroscopy. Now let me look at another benzene vibrational degree of freedom, and here is another one. This is also such that, I mean, you can see that the rings are getting distorted. Okay, almost like the benzene is dancing to the tune of a molecular motion. Again, if you look at it very carefully, there is no dipole moment at any instant of time, because the atoms are exactly oppositely placed as the molecule vibrates. For this atom's position, this is compensating. For this atom's position, this is compensating, and for this is compensating. So there is no net dipole moment during the vibration, therefore this is also infrared inactive. Let's look at another motion which has a large dipole moment. See, all of the hydrogen atoms come down on the plane, but to keep the center of mass of the molecule constant, you see the benzene atom, the carbon atoms go up the plane. If you look at it very carefully this way, you can see it. Let me just rotate the molecule in such a way that you can actually see it. Yes, okay. You can see that with respect to this, that there is a very slight displacement of the carbon atoms above the plane, while there is a large displacement of the hydrogen atoms below the plane, above and below the plane if you look at it. That is, simultaneously a large dipole moment is created in this motion, because there is no compensation between. The dipole moment is created and destroyed, it oscillates between 0 and some value, therefore this is infrared active. Let's look at another infrared inactive motion. Here, this is also a sort of a benzene ring in which some of the atoms, you see it clearly that this 1, 2, 3, the carbon atoms move up while the other carbon atoms move down, and as this carbon atom moves up, the hydrogen atom moves down. These normal modes, there is a very clear mathematical procedure for drawing these normal mode arrows and determining how they should oscillate, and the fact that this is 3n minus 6 or 3n is not magical, there is mathematical structure for doing that. Therefore vibrational motions at the level of very elementary, what is called the harmonic approximation, give you a little bit about the molecular motion. Benzene in a highly excited state, of course, throws away all of these things. This is not going to be the picture, but that's a slightly more advanced part of spectroscopy. Since we are concerned with the basic or the elementary aspects, we will restrict ourselves to the normal modes. So let us look at this, and all of these are some sort of bending modes as you see it. They are low frequency modes. Let us take somewhere in the middle, go to again slightly different frequencies, and what you see is now the bending of groups 1, 2, 3, 4 groups with respect to 1, 2, 3, 4. You see that? So this is slightly more energetic. Go to you can see it using any perspective angle that you want to. Okay, this is probably better to see how the individual atoms are. It's like nodding its head this way and that way. Okay. Let us look at this motion. This is one of the normal modes. Clearly you see these two, they seem to compensate for any dipole changes. These two seem to compensate for any dipole changes, and these two seem to compensate for any dipole change. Do they move? They don't seem to move. There is very little of that, but this is clear that this is unlikely to be infrared active. Yes, it is not detected by infrared spectroscopy. And let us look at a very high energy, one of the most beautiful oscillations of benzene, the symmetric stretch of benzene about its equilibrium position. Okay, this is easier to see. This is like all the carbon atoms shrink while all the hydrogen atoms get extended, and that has to be because this is the center of mass, and the center of mass cannot move in a genuine vibration. We have already removed the translation and the rotational motion of the molecule. Therefore, what you see, that is why this is called a genuine vibration. There is no other contamination by translation and rotation in this kind of motion. So what you see here is obviously molecular motion in which is very symmetric. Throughout this motion there is no dipole moment, therefore this cannot be detected by infrared spectroscopy. How do we do this? The great Sir C.V. Raman found a procedure for determining all the missing vibrational modes of infrared spectroscopy through his procedure of spectroscopy through scattering, and you would see that his is a very complementary spectroscopy to the infrared spectroscopy that was known till then, and every mode that is not infrared active for a molecule which has a center of symmetry will be Raman active. This is the contribution, this is one of the most pioneering contributions by the Indian physicist Sir C.V. Raman, for which he eventually went on to win the Nobel Prize in physics. This is the benzene symmetric mode. Let us see a molecular motion in which there is a large dipole moment for benzene. Here is one example. This is a high energy stretching mode, and you see that the dipole moments add, because when this increases this decreases, which means the dipole moments vectors add and the vectors add, and therefore this has a large dipole moment and it is infrared active. This is a stretching mode. Bond stretching takes much more energy than bending about the bond, than torsion of the ring, and so on. Therefore you see there is a pattern in describing the molecular motion of polyatomic molecules. Torsional motion has small energies, bending modes have slightly higher energies, and the stretching modes, symmetric and antisymmetric stretching, which involve the bond stretching, have higher vibrational frequencies. This is for benzene. Let me give the last example of a very complicated molecule to tell you that this can really go on to any extent. As a last example for today, let us look at TNT, trinitrotoluene, explosive. Hopefully the molecule does not explode on the screen. Let us see what it does when it vibrates. The explosion happens when the vibrations go uncontrolled, and what we have here is controlled very small amplitude oscillations for the molecule. Let us look at a few small amplitude motions and then examine likewise the amplitude vibrations for other higher oscillation, higher energy vibrational motion. What you see here is a very low energy vibrational motion, and it looks like most of the atoms do not move, but they do. In the normal mode approximation, every atom moves from its equilibrium position by a small amount, but it's inversely to its masses. Therefore the toluene group, this is the CH3 group, 2, 4, 6 trinitrotoluene, that's what you have here. The nitrogens are the blue atoms, the oxygens are the red atoms, the carbons are the gray atoms, and the hydrogens are the white small ones. So what you have here is a TNT molecule in which you have a torsional motion of the methyl group relative to the rest of the ring, and to compensate for the effect of this, the rest of the ring moves by a very, very small amount. You can see this in various angles to see that there is in fact a very small motional change in the rest of the molecule. Let us look at the very large amplitude motion. In fact, let us look at the high frequency motion, highest frequency. Let us look at what it does. That is not very interesting. Only 2 atoms seem to be moving away from each other for this motion, but again as you see that the rest of them are nearly stationary because the amplitudes of vibration relative to that stretching of the 2 hydrogens is going to be very small. It is a stretching motion, therefore it has a high frequency motion. And here is the stretching of the methyl group. Here is the stretching again of the methyl group symmetrically here. This is now the torsion, let us look at, yeah, there is a stretching all over the places. This nitro group for example is stretched, this carbon carbon group is stretched. See that this is a very complicated motion. How many degrees of freedom does this molecule have? I will leave it to you as an exercise and will tell you that the answer is 57. Find out why. Okay. Here is another stretching motion. Let us go up and look at that. Yes, here is what you see here is again the stretching of the NO group, okay, and so on. Now the current day computational chemistry programs can pictorially obtain the normal modes of vibration of polyatomic molecules, including several tens and 20s, 30s of atoms and even more. With a little bit of approximate theories, we can obtain the normal modes of vibrations of many atom polyatomic molecules. These are collective motions. I have not had the time to describe the local motion, but we will continue this in the next lecture with a description of the local motion and vibrational frequencies and so on, how we do this in the laboratory. But let us summarize today's lecture by saying that the normal modes of vibrations of polyatomic molecules are the exact analogues of the normal vibrational or the harmonic vibrations of a diatomic molecule, and what we did today is a qualitative description of the vibrational motion with a little bit of about the origin of how they come into effect. There are 3n-6 or 3n-5 degrees of freedom depending on the molecular type, and it is possible for us to view under small amplitude motion all these vibrational motions very accurately. We will continue this in the next lecture to study the local modes of vibration. Until then, thank you very much.